From Kari, Korea, and Dr. Swat from GISTA, Thailand, and me from JAXA. Okay, because we only have 1 hour, we would like to start with JJ from NASA. So please start your presentation.
Check, check. Okay, Sawadee Krap. Good morning, everyone. It's wonderful to be here. This is the 14th MGA meeting, and I think I've missed 2 in that time, and so it's been an honor always to support Satoshi-san, and of course to be here with all of you today. So I have my watch. I have 7 minutes. We have 7 people in 1 hour, so I might be speaking a little bit quickly, but I think that what we want to do is give you kind of a broad view of what lunar PNT is, and of course it's going to be more and more important as the evolution of space exploration continues. And so, with that, okay. So I'm going to thank Joel Parker from NASA for this chart, and really the importance of it is it shows that we are now entering a new era. The space exploration of my generation, I was raised in the 60s and 70s, was a space race. We are more in the Artemis generation, a time of collaboration and cooperation, because no single country can actually do what needs to be done in order to explore and sustain a presence on the moon. And so you'll see a number of organizations that are listed above. We often coordinate ourselves through the International Committee on Global Navigation Satellite Systems, or ICG. There's another important acronym you all should know. It's IOAG, Interagency Operations Advisory Group. And so what these groups do is really take a look at standards development, best practices, and converge, and it's an opportunity for the space agencies to really look at what the technical requirements are going to be. And so because each nation has different objectives, here's where we come together and really discuss where do we find synergies that we can support each other on. In terms of lunar PNT, of course, positioning, navigation, and timing are simply the services that are going to be required in a lunar environment. And so if you look across the slide, we've always done traditional radiometric tracking from the antennas, so Doppler and ranging information. And then, of course, NASA has the TDRS, a tracking data relay satellite system, which is basically a series of geosynchronous satellites that allows us to maintain constant contact for human spaceflight, other applications that are more important for International Space Station, for instance. And then, of course, we're all familiar with GNSS. It was built for terrestrial, maritime, and aviation users, but we are now seeing an evolution of a new space user group being developed, and that's, of course, the space users that are using GPS as standard equipment. And I'll give you a quick example. I used to work at United Airlines. You had to pay money to put GPS on an aircraft. Now you would have to pay not to have it. It's become standard equipment. And if you talk to the satellite operators, most of the platforms that are going up do have some form of GNSS on there. So it becomes our collective responsibility to ensure that the environment they're operating in remains pristine, the spectrum is protected, and my NASA colleague, Kathy Sham, will be speaking about that next. And then we have our pulsar navigation. So just think of this as kind of a galactic GPS, where we're way out beyond where we can get GPS signal coverage. And so pulsars are actually very similar to GPS in that they provide a signal that can actually be tracked if you have the proper equipment. So a galactic GPS is more for deep space operations, and we'll see more of that as we progress from lunar to Mars missions. And then finally, optical navigation. Everyone's very familiar with it. You know, you have a database on your platform, your terrain mapping, and of course that becomes very precise and important as you get closer to these planetary bodies that you may land on, including even asteroids, as you're familiar with our OSIRIS-REx mission that just occurred. So I think many of you have seen this chart in the past, and this is really the evolution of using GPS and GNSS beyond what it was ever intended to do. It's using the energy that spills over the limb of the Earth, but we all know that it's going to be much weaker signal. You're not going to get as good of coverage, and so combining GPS plus Galileo plus GLONASS plus Beidou may give you the best position fix. We already see it on our phones, right? It's becoming standard. And so this is kind of where we're going in the ICG. And again, it's very important to the space segment that we continue to collaborate and share information. GNSS is already embedded into our space operations. What we've been doing is a series of experiments with launch vehicles where we're adding Galileo, GPS plus Galileo, for more resilience. It's something that our national policy says really will assist to take the human out of the loop with some of the launch operations. So we have what's called autonomous flight termination system. You have GNSS. If it strays out of the airspace that it needs to be in, it'll actually self-destruct. So it's becoming more autonomous, and that's kind of the key, greater autonomy. Attitude determination on ISS. We have antennas on the truss of the ISS, and we could actually do attitude determination and have done it for many years. And then, of course, the formation flyer that's up in the corner, this is a heliospheric mission, and it's called magnetospheric multi-scale mission. It's actually halfway to the moon, and we are getting 5, 6, 7 satellites in view. No one ever thought that we would be able to do that. So it now holds the world's record in terms of the furthest going out. But a formation flyer halfway to the moon really opens the door to what may be what may be possible with using GNSS on the lunar surface. In the interest of time, I'm just going to keep going. The bottom line here is we know it's going to be a gradual evolution. We're not going to just snap our fingers and have GNSS capabilities on the moon, but we do have it broadcast in space, and it's something that we can use in the interim. It's an incremental stepping stone until we're able to actually build out lunar architecture. The lunar architecture is going to consist of integrated comm and nav systems. And so this simply shows that it's a progression. This type of application from these systems, we can do many things from satellite servicing to actually being able to operate on the moon. Here's the example. In 2 weeks, I'm going to be at Firefly. We're going to be launching this Blue Ghost lander. This is the first GNSS receiver in history that is intended to operate on the moon. The launch date is going to be in August. If we're successful, it will be historic, first GNSS receiver and signal processing in that environment, and it will set the stage for many other applications. This is just kind of a snapshot of what I just said. Unfortunately, I've run out of time, but I'll just leave it for further examination. And finally, this is kind of a really important chart because it's not just the US and ESA and China. And it really is everyone developing this combination of systems, and it's up to us collectively in forums like this to work together to ensure we understand where is everyone headed and what are the benefits and where are the gaps and where are the synergies. And with that, I'm going to conclude. It's very hard to do a presentation in 7 minutes, but I did my best.
Thank you very much, JJ. Okay. The next panelist is Kashi from NASA. I think she'd be online. Kashi?
Hello.
Hello, Kashi.
Can you hear me? Yeah, can you hear me?
Yeah, could you share your screen slide, or should we share?
I can share my screen. Let me try that. Just a minute. Let me find the screen sharing. Let me see. Where do I go? I'm trying to figure out where would I go to share my screen. Oh, let me look. I do have my slides up on my screen, so I just need to figure out where do. Oh, here it is. All right.
Yeah.
Okay.
Okay, thank you. We are now seeing your slides.
Do you see my?
Yes, no problem.
Do you see my screen?
No problem. So could you start?
Okay.
Thank you.
Okay, you can see my. Yeah. Did you share? You can see it, right?
Yes.
Can you see the screen? Okay, perfect. All right. Well, let me get started since we don't have much time and there's lots of us talking. Following up with what JJ had talked about already, my name is Kathy Sham, and I also work at NASA. My background is in comm. I work in Houston, Texas, home of Mission Control Center. So I started out with Space Shuttle program. I remember the days that we started using GPS. And then JJ also talked about ISS. So that is where I started my career. And so with this, let me move on to the next slide. And hold on, let me see. Okay. All right. So right here, I wanted to quickly follow up with what we were talking about, Lunar PNT. And one of the very exciting aspect of this prospect is that we are going to have lots of systems in orbit, and also we will have systems on the lunar surface. And imagine that all the science that we are envisioning that we're going to be able to do, and the spacecraft that are going to bring these experiments to the lunar surface, we actually will need position and time. And as JJ was talking about earlier already, that the importance of precise time and precise positioning information for our scientific experiments is critical in what we are going to be doing, the unique science that we have not done previously. So the development of in situ PNT service is ever more critical. Let me move on to the, okay, there we go. All right, so this slide is just to give you a quick idea of all the different RF links that we have already been working on and in planning stages. And basically, the ones that I highlighted in yellow are the ones that we have worked on with our space agency partners, in particular for the last several years, through the Space Frequency Coordination Group, which I will give you a little more idea about. We have already identified 2 gigahertz spectrum at 2483.5 to 2500, where we would look to develop this in situ capability for missions that are going to be operating in the vicinity, including those on the surface and those that are traveling to the lunar orbit and will be orbiting around the moon. And of course, there was going to have to be a transition from the Earth-based GNSS moving into this new capability that we're looking for. Not only space agencies, but in the future, potentially having more satellite-based capabilities with other commercial partners even. So those would be operating initially in the 2.4 to 2.5 gigahertz range, and that's where we envision for the system to operate. And also that we are currently studying 5 gigahertz frequency range for future expansion. So, and as you can see that today, for Earth-based, we also have multiple GNSS systems that are sharing the same frequency band that are offering this capability. So with that, let me move on to the next slide. Somehow it's not moving. Oh, there we go. Okay, lunar spectrum management. This is a term that we started using a few years ago because this is something that we felt that based on our past experiences cooperating between space agencies, it's very critical that we all work together. And as JJ said already, that we are this time around going to go together globally with many partners rather than going alone. It's not a race, but a collaborative effort that we have scientific community, commercial community, U.S. And our government agencies and other administrations and their efforts. And so everyone, we wanted to make sure that everybody would benefit from this exploration effort. And so we are leveraging what we learned before to take it forward. So with that,
same problem with what we had with the other one.
Sorry, could you mute?
The SQL server,
Sorry, not Kashi. So everybody connecting Zoom, could you mute?
It is running on the SQL server though.
Capri, could you mute?
I think maybe even on the TPP
This
server.
is the SQL server. This is the SQL server, right?
Could you mute,
Yes.
Capri?
No.
So the activation service is not running, but it is running on the encrypt. On the
Can you
encrypt
start?
server, it is running.
Can you start this?
Okay, Kashi, you can start. Kashi, you can start. Kashi, please start.
okay, all right, so, okay, okay, can you hear me again? All
Yes,
right.
no problem.
So I am on the slide, but okay, somehow
Kashi,
I'm
you
not
only
seeing
have
my
1 minute.
slide
Kashi, you
advancing.
only have 1 minute.
Okay. Okay, so let me go ahead and just talk real quick about Space Frequency Coordination Group. Space Frequency Coordination Group is a group of civil agencies, and we work together for many, many years together to advance our collective missions. And one of the most important things that we are actually doing right now is working on a future agenda item in the ITU to ensure that we have protected spectrum that I talked about, 2.4 to 2.5 gigahertz range, so that we could support the lunar PNT development. So let me just stop there, and my slides are available, so please feel free to go through them later. Thank you so much.
Thank you, Kashi. Okay, our next panelist is Dr. Jianming from Cary.
Thank you, Dr. Russell. Good morning, everyone. I'm Jung Min-ju from Korea Aerospace Research Institute. Thank you for the opportunity to introduce our activities related with Lunar PNT and the MJ conference. Republic of Korea has the ambitious goal of becoming a space economic powerhouse by 2045, and to achieve this, the First Space Development Promotion Based Plan for implementing the future space economy roadmap was established in December 2022. Among the 5 key missions outlined in the plan, the first mission is to expand space exploration. The specific targets include a lunar landing by 2032 and Mars landing by 2045. In line with the goal of strengthening international cooperation for space exploration, we have been actively participating in the Artemis program led by the United States since 2021. Reflecting the significant national interest in space exploration and space economy, Republic of Korea is planning to establish the Korea Aerospace Administration.
不过能放进来，如果还有东西，这就想别的办法，最好找个稳定一点。好，稍等，我看看啊。
Okay, please mute everybody. Sean Wang, please mute. Okay, please start.
Okay. Okay, yeah. In August 2022, we achieved a significant milestone in lunar exploration by successfully launching the Korean Pathfinder Lunar Orbiter (KPLO) over the Falcon 9. This marked a crucial step in our nation's lunar exploration efforts. As you might know, KPLO did even better than expected. It successfully entered the lunar orbit through the PLT orbit for pure efficiency. KPLO has been performing its mission reliably beyond the expected lifespan. Sorry. Looking ahead, we aim to initiate the development of a lunar lander this year with plans to launch it using our own technology and next generation launch vehicle by 2032. This marks a crucial step forward in enhancing our lunar exploration capabilities. In addition, since 2022, we have been actively engaged in the development of the Korean Positioning System, KPS. The plan is to establish a regional navigation satellite system comprising 3 GEO satellites and 5 IGSO satellites by 2035. If this happens, it is expected that the KPS signal will be able to use in the Lunar PNT system currently under development. Space exploration, including missions to the Moon and Mars, holds great significance to humanity's sustainable prosperity and peace. The Republic of Korea is committed to a long-term space exploration plan aiming to enhance its independent capabilities while strengthening global cooperation in space development. The lunar PNT system stands a core element of lunar exploration and lays the foundation for Mars exploration. We look forward to collaborating with international partners in its future development. Yeah. Thank you for your attention. Thank you.
Okay, thank you very much, Dr. Jong-min. Okay, next presentation is from Javier. Javier, are you online? Yeah, please unmute your mic.
Hello?
Hello,
Can you
I
hear
can
me
hear
now?
you. Yeah, could you share your slide?
Yes.
Okay, thank you.
You confirm me when you see those?
Yes, we are now seeing. Please proceed.
Okay. So, very good morning. Pleasure being in this panel with such good colleagues. So I am going to talk about the Moonlight Lunar Communication and Navigation Service, which we are developing at Europe, at the European Space Agency, together with industry. As in the title you can see, it's a new paradigm in lunar exploration. This is the mission of Moonlight, to deliver a service, is really a service of communication and navigation for both commercial services, but also institutional services. We aim at supporting Artemis, supporting ESA missions, but also providing possibilities for people who are willing to have lunar missions, to have communication and navigation services, and then to have the possibility to buy those services. That's the vision of Moonlight. You can see here the services we are providing. We are integrating communication and navigation into the same service. We see how important is that on the Earth. So we are convinced it is the way to go. We will provide high data rate in K-band. We also provide communications, telecom operations, and audio and video streaming. We also have communications in S-band, and then position, velocity, and time precisions, a GNSS-like service with an initial operation, as I will explain, in 2027, and a final operation in 2030. You see here a little bit the schedule of the planning. You see the picture here, it is the moment, it's a very historical point where the ministers of the ESA member states approve our mission. It was last year in November, so we are starting exactly next week the implementation phase with industry. We are starting what we call the phase P2CD, so aiming at initial services. It will be a communication and initial satellite of navigation in 27, and as I mentioned, the full operational, the complete service should be by 2030. This is the service area where we are proposing our services during the next 10 years, 15 years, from 70 to 90 degrees south. And then you can see 200 kilometers height. This is the landing space. And we are also providing, of course, a service for a low lunar orbit as well. And you here can see a little bit in a summary the requirements we have for position, velocity, and time. This is the requirements. We have 100 meters real time in orbit, landing below 50 meters in real time, and surface operations of the order of 10 meters or better. You have here in this slide the example of constellations. We will be elliptical lunar frozen orbits. You can see the initial constellation of 4 satellites. This is an example. Industry is now doing the final tuning, but will be very similar to that. 24 hours orbits guaranteeing that we have a minimum, as you can see here, of 15 hours of continuous navigation every 24 hours in the South Pole. These 15 hours are fully predictable, and the system will be very similar, very similar to the GNSS we have on the Earth, with similar complexity receivers. This slide illustrates on the bottom the actual performances we are simulating with a very accurate simulations, and on the top the requirements we have. I will give you now some details on the performances we are assessing today, and this is the result of very thorough simulations, really emulating almost end-to-end our system. The first one I am going to emulate is a typical landing using Moonlight. As you know very well, landing is the most delicate operation in lunar exploration, with only 50% more or less of successes. And this is a typical landing profile, the typical 1 hour operation with the final pitch up maneuver, which is the moment we are approaching. We emulated our example in this place in Connecting Ridge, which is one of the areas proposed for Artemis 3 to be representative. And you can see in this slide The typical performance we get, it is the order of 19 meters, 20 meters. This is the accuracy we get with a very simple altimeter and a very simple IMU. We don't have a Doppler radar, we don't have visual cameras. It's really a change of paradigm. This will allow, for example, landings in permanent shadow regions where you cannot normally use optical visual, and also landing on the other extreme in peaks of eternal light, places where you need to have a very high accuracy. Let me show you a couple of results more. Combining with rover sensors, our analysis, again, very thorough simulations, illustrate that this initial constellation should be able to provide typically 3 to 5 meters in the lunar surface, only using moonlight and a digital elevation model information. Only that, 3 to 5 meters real time, much better in the post-processing time. And an area where we are working a lot now is extensively, it is the area of local differential. So we are showing, and we are working, as I mentioned, with a lot of effort now, that a single station, which could be combined with one of our landers, for example, Argonaut, could provide an augmentation to the moonlight and could provide a service to the whole South Pole. We are demonstrating that with our analysis with performances below 1 meter accuracy using moonlight and differential corrections, which are provided through the moonlight navigation channel. So any user in the area in the South Pole may benefit from this service because of the absence of iono, the correlation of the error, the correlation is very low. I finished by mentioning the importance that ESA is giving to international cooperation. We are working with NASA and JAXA in the international standards LunarNet, and very importantly, we have advanced very, very much in the standards on the signaling space description for the LunarNet PNT signaling space. It is important to note that today, with the level of definition we have, we can start building already receivers LunarNet compatible. And this is my last slide, just to illustrate this interoperability test we are planning to do together with JAXA and NASA. This could be by 2028 when we have our initial showing that together we can provide a service and showing that we can demonstrate interoperability. This is the way we think we need to go, and we are very willing to cooperate with other space agencies. Thank you very much, Masaya. This is the end of my presentation.
Thank you very much, Javier. It was a wonderful presentation. Thank you very much. Okay, the next panelist will be from GISDA, Dr. Swat.
Good morning, everybody here and in the online channel. It was my great opportunity to be here in this panel. I was here last year as well, and by that time I can learn many things. I mean, from because I'm relatively new to this field of the lunar PNT system. And by that time, I have learned that we also, in the global area, we also try to complete try to develop this technology as well. Then, by that time, I have a wonderful time talking with the people here, and also some of panelists here as well. And then I go back to my office and try to survey into the Thai Research Society. How do we have any researcher that are interested in this topic, this idea? And I found that it's pretty hard for me to find a researcher to do this topic. But there are some people. There's some people that are working on the space technology, really interesting in this idea, even in GISDA as well. So I try to stimulate a little bit, accelerate the interesting in this topic for the Thai area. Can I have the? Then. Yes. then I go back to my organization. My organization is a space agency in Thailand, and then my executive director he want to develop the new space economy in Thailand, and one thing that they made that is among five topics that he emphasized is a space for future mankind, and in that for space for future mankind he actually we emphasize on two things. One is space experiments and space experiment, moon and Mars exploration, and another thing is spaceport. So it means that this topic is already emphasized by my organization, and then we want to accelerate on this topic. And earlier we play the role as a facilitator for this topic, and then we try to gather around the researcher and then try to make a suggestion to Thai policymaker about the topic that we have. So one thing that we are doing in the previous year is we try to develop a white paper about the space research in Thailand, and in those areas that we try to push is this space exploration and utilization. So in that plan, we wrote a white paper, and then we gather around the researcher or in Thailand who work in this field, and so we propose this topic to the Thai funding agency to set it as the strategic plan for the Thai researcher. And now we have some progress to tell people here is that now this plan is taking into the seriously consideration of the funding agency, and also the funding agency set up a researcher team to investigate all the topic that we have proposed in that white paper. So even though we don't have that much progress as we see from the another panelists, but we try to initiate this topic into the Thai researcher area, and then we really glad if we can be the focal point to connect the global researcher with the Thai researcher, and also the reason I am here today is I want to reach out to the research society on this Lunar PNT field that Thailand that we need collaboration, because we cannot start from the scratch, and we try to connect those two together. And one thing that the funding is also important, and another thing that GISDA doing now is try to push this topic into the Thai funding agency, and now they are taking about this topic seriously. So that is the key message that I want to present to the people here in this panel. Thank you very much.
Thank you very much, Dr. Swart. Okay, let's move on to the next panelist from China. Xiaomen, could you share your presentation slides?
Okay, can you see my presentation?
Yes, we are now seeing. So please start.
Okay, wait a minute. Okay. Thanks for the invitation from Messiah. I'm from China Academy of Space Technology. Today I'm going to talk about some consideration of the Earth-Moon Integrated Network specification. Okay, my presentation includes 3 parts. First, from the background requirements, now China has already developed the Beidou navigation constellation, and also is initiating the construction of a low orbit communication constellation. And in the future, so there is a need to achieve interoperability of cross-domain spacecraft to enhance the benefits of comprehensive applications. And in the deep space exploration, we have the Chang'e 4. And also from the right side, you can see that we have a Chang'e 1 relay satellite, which can provide communication service from the back of the moon to the Chang'e 4. And also in the coming year, China will continue to carry out a lunar exploration project, such as the Chang'e 7 and the Chang'e 6. Chang'e 6 will take samples from the far side of the moon, and the Chang'e 7 will land in the south polar of the Lunar. So for the major requirements, we have three requirements. First is communication. Is to increase the coverage capability of the moon and also the other planets. And also the second is the positioning, is to support the activity on the moon and the positioning also of the astronauts. Before the 2030, China will also have the manned lunar project, which will send 2 astronauts to the moon before 2030. And also for remote sensing, is to support the location selection of the International Lunar Research Station in the future. So we have these 3 major requirements for the constellation. And from this figure, you can see that this is what we can seek to build in the future. Is Earth-Moon communication and the navigation, and also the remote sensing is like a constellation around the moon. Which include several satellites on the ELFO orbit, and also some satellites on the L1, L2, and other orbits. And also there is a requirement to uniform the television telecommand, and also we need to simplify the application, and we need to have efficient telecommand. So this all will need the standardization of the protocol between the different satellites and the satellite and the ground. And also we need to have a shared messaging mechanism, which may include the subscribe, publish, and also send receive. This is to have this information sharing mechanism among both the space network and also onboard network. So to summary, in the future, we will have a Earth-Moon integrated network. And also we need to have a uniformed intra-network, which is inside the satellite. And also we need to have standardized protocol architecture between the spacecraft and the ground. So the key is the protocol architecture of this Earth-Moon integrated network. We can see that there are several related specifications. The first one is the 6SDS, which has already developed a space communication protocol architecture, which is divided into 5 layers, which is application layer, transport network, backend, and physical layer. And currently, this protocol architecture is still evolving. And also, we have another onboard communication protocol architecture, which is divided into 4 layers. This is not the same as the space communication protocol architecture. Currently, it still need to be evolved in the future. And also, we can see that from ESA, that they have the ECSS standard, which can be compatible to this CCIS standard. It have like the POS and also the some onboard communication standard. And from the ground view, we have the IETF, which has developed a lot of protocol that's used in the ground internet. And China is now developing the whole system built upon the IP version 6 network. And we also have like, you can see that NASA and ESA, they have developed the Lunar Night interoperability specification document. They also have some frequency plan and other protocol architecture. From this view, we have like some kind of problem suggestions. First is currently the space and the onboard communication protocol architecture is not uniform. So I think we need to develop a unified smooth network protocol architecture to facilitate the interoperability and information sharing. This is the protocol architecture that we propose. And this is architecture is divided into 4 layers, which is application layer, transport layer, and network layer. And below the network layer, we call it sub-network layer. This is different from the internet satellite communication and the inter-satellite communication. From the inter-satellite communication, we can see that they use a lot of CCIS currently used, such as telecommand, advanced optical system, and also the next generation of the unified space link protocol. But we may need to develop some dynamic access protocol. And from the onboard view, we can see that we use the packet service, memory service, to isolate the difference between different onboard data links, such as the 1553 and other high-speed bus protocol. And from the network layer, we have both the space packet protocol to support the low-speed spacecraft to ground link and also onboard link. And we use the IP, especially IP version 6, to build a bridge between the onboard network and the space network. From the transport layer view, we can also use the TCP UDP and also the FTP from the DTN protocol suite. And in the application layer, we can integrate both the ECSS POS service and also the AMS BP CFTP from CCIS.
Sorry to
and
interrupt.
other.
You have only 1 minute left. 1 minute left.
Okay. I'm almost done. Okay. So this is the first suggestion. And the second is that currently the X-band is not considered as a relay link between the relay satellite and the users. So we suggest that the X-band can also be used for both Lunar relay and Earth communication in order to facilitate this weight savings. But this is the Treasure 1 example. It has the X-band to this Chang'e 4 satellite. And also the problem 3 is that the L-band is also not considered as the Lunar PNT band. Currently, around the Earth, we use the L-band. So is that possible that we can also consider this L-band using around the Moon? So these 3 suggestions. Thank you.
Thank you very much, Shomens. Okay, so the final panelist is me. So could you share? Okay. Thank you very much, everybody. So my name, the title of my presentation is Japan Lunar Navigation Satellite System (LNS) and its contribution towards the Multi-GNSS. My name is Masaya Murata from the Japanese Space Agency, JAXA. And our JAXA Lunar PNT system called LNSS was designed to become a GPS-like satellite constellation for the Moon. And this slide shows the satellite constellation. And we will use 2 stable Moon orbits called elliptical lunar frozen orbit, ELO4. And for each ELO4, we will deploy 4 satellites. So the total number of the satellites becomes 8 for our LNSS. And this LNS satellite will broadcast one-way navigation signal for lunar user in a similar way to the GPS. And our initial service region will become the lunar transport region, same as ESA NASA lunar PNT system, where the U.S. Artemis base camp and the global exploration will be expected. So our LNS also function as a data relay satellite between the Moon and the Earth, but my presentation today is focused on the PNT aspect. So to provide the PNT service for lunar users, the orbit and clock information of the LNS satellite should be determined as accurate as possible. So we have investigated several approaches, but our current designs focused on using the GNSS weak signals. As shown in this slide, because the GNSS satellites all pointed towards the Earth center, their navigation signal that passes the umbrella of the Earth will only reach the Moon region, and our LNS satellite will be navigated based on these GNSS weak signals. And according to our simulation results, the signal in space error CC of about 20 meters can be expected by this approach, and this approach makes our LNS highly autonomous because the amount of the Earth station operation will be dramatically decreased. So JAXA, European Space Agency, ESA, NASA are now working towards the establishment of the Moon GNSS called LANS, a Lunar Augmented Navigation Service. LANS, the concept of LANS is shown here. The point is, even though Japan, Europe, US satellites will be developed and deployed by different agencies, companies, all of these satellites will broadcast the standardized navigation signal called the Augmented Forward Signal, AFS, to form the LANS. So in this way, the lunar user will not have to differentiate each system, and the interoperability among these respective lunar PNT systems will be guaranteed from the get-go. So this concept is quite important because it is challenging to deploy the sufficient number of satellites on the Moon by each space agency. So through this international cooperation, we can actually provide the high accurate PNT service for lunar users. So this photo was taken at the Lunar PNT panel session at the ION GNSS Plus last year. And in this panel, representatives from NASA, ESA, JAXA provided their respective lunar PNT system and the lunar PNT standardized document called LunarNet Interpret Specification and a status of our current ongoing international collaboration. So the second person from the right is me, and it was a great honor to participate in this first ever Lunar PNT panel with the Lunar PNT experts from ESA and NASA. So JAXA are now planning to do the launch demonstration mission in 2028, and we are now planning to launch and deploy our first LNS satellite and launch receiver to the Moon. And this slide shows the asset deployment overview. Using JAXA rocket and Japanese small lander, we will deploy our first LNS satellite in the Moon orbit, ELO4, and we will also place the launch receiver at the lunar South Pole region. Using this mission, we are now proposing the first ever ESA NASA JAXA launch interoperability and the PNT demonstration. At the year of 2028, one ESA satellite and a few NASA satellites can be expected in their Moon orbits, and using the launch receiver to be located at the South Pole region, the augmented forward signal from these satellites will be received, analyzed in the actual Moon environment to prove the launch interoperability. And using this mission, we are going to also evaluate the lunar PNT accuracy achievable by the launch concept. So to conclude, the JAXA LNSS, ESA LCNS, NASA LCRNS will comply with the LunarNet interoperability specification and together form the launch that becomes the Moon GNSS. And these three space agencies encourage the launch interoperability demonstration mission in 2028 and are currently assessing their respective participation. The launch receiver to be located at South Pole region will receive all launch augmented forward signal and send them back to the Earth for the in-depth analysis. And in this mission, a laser reflector LLR will be placed on the Moon surface as well for the precise position estimation of the launch receiver. And we expect that these laser ranging data will be also utilized for the refinement of the Lunar Reference System, LRS. That's it from me, and thank you very much. Okay, so all the presentation from panelists was finished, and we would like to move on to using the 6 minutes. We would like to move on to the question answering. So the first question actually comes from me. The first is this one. the effort of guaranteeing the interoperability among respective lunar PNT systems is currently ongoing. And for example, the international collaboration to form the Moon-GNSS lens is in progress under the international frame called the LunarNet. So what will become the key issues for accomplishing such an international lunar PNT systems? So I'd like to start with JJ, if you have a comment on the interoperability.
Well, thank you very much, Messiah. I would say that just quickly, the most important thing is the continued transparency and collaboration that's been established within some of these forums that we've talked about. We're all going to have different objectives, but in the end, we're trying to build infrastructure that serves everyone. And so we need to maintain what we've started, this very positive progression towards building out the infrastructure. And I would just say it's up to all of us at our level to make sure that our senior leadership continues to bring that positive message forward.
Thank you very much. Cassie is still online?
Yes, I'm here.
Yeah.
One of the things that I wanted to follow up is obviously from a radio frequency spectrum perspective that we want to make sure that we have protected spectrum. As we all have learned in our past experiences that GPS is actually fairly weak signal, and that careful planning and management of the spectrum that are being set aside for the service on the moon is ever more important and critical. So that is one of the biggest things that through international collaboration and support, we now have an opportunity to secure some spectrum that everyone could use for lunar PNT at the World Radio Conference in 2027. So it's a very positive thing that we were able to do together during the World Radio Conference 2023. And now we have work to do to be able to secure that spectrum. Thank you.
Thank you, Kelsey. Dr. Jungmin, you have any comments on this?
Yes. Personally, I think that it is crucial for the development of the lunar PNT systems in each country to proceed smoothly according to the agreed upon schedules, considering interoperability. Otherwise, we might run into some like worries about the delays and building the system and other related issues. So to prevent this, I think it is important to set up some clear technical standards and encourage tight information sharing and technical cooperation among all participating countries. Thank you.
Thank you very much. Javier, are you online?
Yes, I am online. Can you hear me well?
Yes. Could you provide your comment?
Yeah, very good. So first of all, I think this is a very important point for Europe. For ESA, it's a super priority to ensure that we have interoperability between our systems. We are working, as you know, very, very intensively in this LunarNet initiative. We believe this is an excellent initiative. We are working with the IOAG, with the CCSDS as well. So it is very important that we have other countries joining. We are very welcoming the initiative and comments from other space agencies. For us, it's very important that our systems, they have the LunarNet compatibility as a mandatory requirement. This is the case for Moonlight, and I understand also for the NASA and the JAXA ones. So then this will ensure we are designing the systems against the same standards. Very important that we finish these standards now. We are very close, that we are able to develop receivers already. And I think, Masaya, your proposal of this interoperability test as early as 2028 can be extremely important to demonstrate this works and then to be really a triggering point that our future evolutions maintain this interoperability. So very important point, and with the comment with Dr. Miller, I fully support the transparency and the interest to have also other countries supporting our LunarNet. Thank you very much.
Thank you very much. Dr. Swat?
Yeah. For me, the interoperability is kind of is important. The key that we can achieve this, I think, if we keep exchanging the technical knowledge to each other, we can work together on this on this standard, and then I think everybody want the achieve the kind of a similar goals, but maybe have some slightly difference in the small objective. But if we keep exchanging and keep make this kind of opportunity happen over and over again, and we can guarantee on this interoperability. Thank you.
Thank you very much. Showman, you there?
Yes. Okay. I think the most important thing to support the interoperability, there are two things. The first is the consistent frequency design, that we need to consider the future lander and also maybe moon orbit satellites, their frequency requirements, including both the communication and the navigation. So this is one of the things. The other thing is that we need to have a uniform protocol architecture to support the information sharing between the satellites and also maybe landers from different organizations. Okay.
Yeah, thank you very much. So my final comment is lunar PNT is certainly a challenging problem, but through the international collaboration, I think we can achieve to provide a high accurate PNT service for lunar users. So the international collaboration will be definitely a key aspect, and we are already doing such international collaboration, for example, between JAXA, ESA, and NASA. So we'd like to see its expansion to include other countries as well. And so using this kind of workshop and exchange idea and comments, and this kind of opportunity is quite important. So I think that's it for the time, 11 a.m. So thank you very much again so please conclude with applause. Thank you very much.